Welcome back to EGME-333, Fluid Mechanics. This video will talk about the Newtonian fluid model. So let's begin by discussing the viscous flow over a flat plate. To do so, we'll track the position of a set of fluid elements. We'll have the red fluid element labeled A, the green fluid element labeled B, the blue fluid element labeled C, and lastly the orange fluid element labeled D. Initially, at time equals 0, all fluid elements are placed at the leading edge of the flat plate, which corresponds to the x equals 0 location. As the flow travels downstream past the plate, the fluid elements propagate with the free stream. It's observed that the further away the fluid element is from the surface of the flat plate, which corresponds to y equals 0, the more the fluid element travels in the x direction. Its position x is equal to its velocity little u times the amount of time passed, delta t. So little u, the velocity in the x direction, coincidentally depends on its vertical position y. So u is a function in y, where we observe that the velocity in the x direction increases with the y position. Now, instead of focusing on the position of the fluid element, let's now focus on the deformation of a fluid element that is subjected to this velocity profile u as a function in y. So again, we'll consider a set of fluid elements starting with fluid element A shown in blue, fluid element B shown in green, and fluid element C shown in red, where C is closest to the surface of the flat plate. We assume that each fluid element at time equal t0 is going to be the shape of a perfect square, where both the width and the height of the fluid element is going to equal a distance delta y. Now, because the velocity in the x direction little u varies with vertical position, we can imagine that the upper surface of a fluid element will have a different local velocity than the lower surface of the same fluid element. For example, if we focus on fluid element A, the blue one, we can assign a velocity to its upper surface, which we'll label as u sub A upper, and a velocity to the lower surface of the fluid element, which we'll label as u sub A lower, where because of the variation in the velocity profile with vertical position y, then there must exist a difference in velocity between the upper surface and the lower surface, which we represent with delta u sub A, which is equal to the difference in velocity between the upper surface and at a fluid element A minus the velocity at the lower surface of fluid element A. In a similar fashion, fluid element B also experiences a difference in velocity between its upper surface and the lower surface. However, this difference is much more pronounced. And similarly, fluid element C experiences this velocity difference. However, the difference between them gets bigger, where the general observation is that the difference in velocity between the upper surface and the lower surface gets bigger as the fluid element is closer to the surface of the flat plate, which corresponds to position y equals 0. So what type of deformation does the fluid element then experience because of the difference in velocity between the upper surface and the lower surface? So if we monitor the shape of each fluid element, then we can observe that as time increases from t0, that all three fluid elements are going to experience some form of shear strain, where fluid element C will experience the largest amount of shear strain and fluid element A will experience the least amount of shear strain, as illustrated by the red and the blue elements respectively. So a natural question arises: how do we quantify this deformation? And we can do so by utilizing this angle theta, which will correspond to the angle of deformation. For fluid element B, we can represent it as theta sub B. For fluid element A, it will be theta sub A. And lastly, for fluid element C, we'll represent it as theta sub C. Now, in fluids, we're much more interested in how fast something deforms, the deformation rate, rather than how much. So we want to quantify the deformation rate with the shear strain rate, which is given to us by the rate of change of the angle theta with respect to time, d theta dt, or theta dot. So how does then the velocity profile u as a function of y relate to the shear strain rate theta dot? We can zoom into this triangle. We'll replace theta sub b with simply theta, and recall that the height of the fluid element was delta y, and at the opposite edge, its length corresponds to the difference in velocity between the upper and the lower surface times the time, delta t. We can utilize trigonometry to show that the tangent of the angle theta is equal to delta u times delta t over delta y. By using a small angle of approximation, where the tangent of the angle theta can be approximated simply as theta, then we can simplify this expression as the angle theta is approximately equal to delta u times delta t over delta y. If we rearrange this equation by dividing delta t across and rewriting theta as delta theta, we can consider the limit where delta t approaches 0, and similarly where delta y approaches 0, and this expression simply becomes that d theta dt is equal to du dy, where in essence the shear strain rate theta dot is equal to du dy, the rate of change of the velocity profile little u with respect to its vertical position y. Now let's imagine that for each fluid element we can measure both the shear strain rate du dy and the corresponding shear stress. So if we plot them on the same graph, here we'll place the values for fluid element A, fluid element B, and fluid element C. If we fit a curve between these 3 points, we can see that the shear stress is linearly proportional to the shear strain rate. To equate them, we can consider the slope of this line, which we'll label with the Greek letter mu, and argue that the shear stress tau is equal to the slope of the curve mu times du dy. So any fluids that experience this linear relationship between shear stress and shear strain rate, these are fluids that follow Newton's law of viscosity, which we often refer to as Newtonian fluid, where the slope of the curve corresponds to the dynamic viscosity of the fluid. So for a Newtonian fluid, which follows Newton's law of viscosity, the shear stress tau is equal to the fluid dynamic viscosity mu times the shear strain rate du dy. Any fluids that do not follow this behavior are what we often refer to as non-Newtonian fluids.